Dear students, in this video we are going to discuss about the metallic carbonyls. So what are metallic carbonyls? Metallic carbonyls of the coordination complexes, some type of coordination complexes which are coming under the organometallic compounds in which one or more metal centers are present, and those metal centers are surrounded by carbonyl ligands. Now, let us concentrate on the bonding between metal center and carbonyl ligand. So, we are going to discuss the bonding nature between the metal center and carbonyl on the basis of molecular orbital theory. So, we know that metal is coordinated with the carbonyl. Here, the carbonyl is having the bonding nature in this manner. That means a pair of electron is present in the sigma bonding orbital of the carbonyl carbon. Okay, we know that carbonyl is an ambidextrous ligand. In this ambidextrous ligand, carbon is acting as a donor atom, and we know that it is filled bonding molecular orbital with sigma symmetry. Okay, and let us take metal. In metal, it has d orbitals. Among the 5 d orbitals, 2 orbitals are having sigma symmetry. So according to molecular orbital theory, that means Eg star is higher energy and somewhat anti-bonding molecular orbital nature, so that it is purely empty in nature. There are 4 lobes, which is dx square minus y square. It is empty. Since dx square minus y square is empty in nature, the electrons from the carbonyl carbon will be transferred this empty anti-bonding orbital of metal. Okay, you know that the empty anti-bonding molecular orbital should not accept electrons. If it is accepting electrons, what will happen? The molecule will be getting destabilized. Okay, however, as soon as it is getting the electrons from the carbonyl carbon, it forms a sigma bonding. So according to the coordination chemistry, it forms the sigma bonding. Meanwhile, we have filled T2G orbital of metal. Filled T2G orbital with the pi symmetry, it is getting filled in nature. So according to molecular orbital theory, you know that it is filled T2G with the pi symmetry orbital. Okay, so as soon as the dx square minus y square is getting electrons from the carbonyl carbon, the filled T2G orbital will be donating its pair of electrons to the empty anti-bonding molecular orbital of carbonyl carbon. Okay, since the electron is transferred through the pi symmetric, it forms a pi bonding. Okay, but after getting the pi electrons from the T2G of metal to the anti-bonding, the molecule will be looking very unsafe. That is, this molecule is going to be destabilized. Therefore, the so-called received electrons through the pi bonding will be getting down to the empty bonding molecular orbital of carbonyl carbon. Okay, so in this manner, the sigma bond will be formed and it is strengthened by pi bonding, and the pi bonding which has been formed is strengthened by sigma bonding, and this process is continuous process and it will be going on. Okay, therefore, if a metal is forming a bonding between carbonyl carbon, we can have two bonds, one is sigma and another one is pi, but these two bonds are not a stable one, are not a constant one. If you take alkene, we have sigma bond and pi bond between the two carbons. Okay, both of them are static bonds, these are static bonds, but here the sigma and pi bonding between metal and carbon are not static in nature. Okay, that means if sigma bond will be formed, then pi bond will be followed. If pi bond will be formed, then sigma bonding will be followed. Okay, this type of bonding, non-static bonding approach is known as synergic effect. This is known as synergic effect. Okay, so we should not misunderstand that once the sigma bond has been formed, the pi bond will come and it will weaken the sigma bond. It is not at all. Once sigma bond has been formed, then pi bond will be formed, so that the bonding between or the metal carbon interaction will be more and more strengthened, so that no outside ligand cannot touch, cannot approach this metal as easily as possible. Okay, so this is known as synergic effect, and moreover we can have the another bonding, another names for this bonding, back bonding. It has been also called back bonding. Okay, since metal is giving its electrons through T2G, T2G means dxy, dyz, dzx. Since the metal which has T2G filled orbitals and it is donating its pair of electrons to the anti-bonding orbital of the carbonyl carbon through pi, therefore this entire carbonyl ligand will be hereafter called pi acid ligand. It is known as pi acid ligand or pi acceptor ligand. Pi acceptor ligand. Okay, so these are all some other names of this uh, uh, the bonds which is the ligands which is involving in the back bonding. Okay, so what will happen? So how can we characterize there is the possibility of back donation, how it was taking place? Okay, so this can be characterized by or confirmed by IR spectroscopy. Okay, we know that carbonyl will have triple bond. Okay, if metal is electron rich in nature, suppose this metal is electron rich, this metal is electron rich, what will happen? This carbonyl carbon is donating a pair of electron to the metal. Since this metal is already electron rich in nature, this will receive electron so that it becomes more and more electron rich. So it cannot bear the more electron rich density, therefore it will push away the electron to the carbonyl carbon. That is, the more electron density will be given again to the carbon through back donation. Okay, as soon as formed the sigma bonding, it will form pi bonding. Okay, as soon as this carbonyl carbon is getting more electron density, the carbonyl oxygen bond will be getting reduced. Okay, so this impact, this effect, this carbonyl carbon oxygen bond reduction will be shown in the IR frequency. In the IR frequency, we know that carbonyl stretching frequency, carbonyl stretching frequency may be 1700 centimeter inverse. If the back donation is taking place effectively with more electron rich metal, then what will happen? The carbonyl oxygen bond reduction will be taking place, so that 1700 centimeter inverse is not observed. In fact, less than 1700 centimeter inverse of carbonyl stretching frequency we can observe. Okay, so let me tell you in the simple way. If you take the carbonyl, if you take the IR frequency, IR spectrum, suppose you get 1700 for free carbonyl. Okay, it is for free carbonyl stretching frequency. But suppose this carbonyl carbon is making a bond with the metal, then what will happen? The IR stretching frequency will be observed little earlier of 1700 centimeter inverse. Okay, it may be observed in what is called 1650 or 1625. So in this range it will be observed. So dear students, I hope you might have understood very clearly about the bonding nature of the carbonyl carbon. That means metal carbon bond nature. Suppose, yes, I forget to tell you one more thing. Suppose if you take the metal which is electron deficient in nature, that is electron poor metal center, what will happen? Since the metal is already suffering with the electron poor nature, therefore what will happen? If it is getting electron from carbonyl carbon and forms a sigma bond, since it was already suffering from electron deficiency, it will accept the electron, but it will donate less effectively to the carbonyl carbon. Therefore, the bond reduction between carbonyl carbon and oxygen is somewhat less. Therefore, we may observe the carbonyl stretching frequency less than 1700. Okay, no different opinion, but we cannot observe too much decrease of 1700. Okay, if back donation is taking place with the electron rich metal center, what will happen? If electron rich metal center, then what will happen? We can expect 1650. So in this range, 1600, in this range we can expect. But if you take the electron poor metal center, what will happen? We can expect 1675 centimeter inverse, 1680 centimeter inverse, 1690 centimeter inverse. So in this range we can expect. Okay, so dear students, I hope you would have understood more clearly about the bonding nature of the carbonyl metal carbonyl compounds. So let us move on to the next topic called the metal carbonyl compounds.